Good morning. Good morning, ma'am. My name is Jeevam Jagisha. I am studying in CSCC section. Today, my topic is asynchronous upcounter 2-bit, 3-bit. Introduction to asynchronous upcounters. Asynchronous upcounters are digital circuits that count in a upward direction. They operate without a common clock signal, meaning their flip-flops do not change synchronously. Their counters are widely used in various applications, including timers and frequency dividers. Basics of counting. Counting is an essential function in digital electronics used for various purposes. It is an essential function in digital electronics used for various purposes. Upcounters increment a binary value with each clock pulse moving from one state to the next. The counter sequence is determined by number of bits in the counter, which affects its maximum count. Upcounters increment a binary value with each clock pulse. It is determine the value of bits in the counter, which affects its maximum count. 2-bit asynchronous upcounter design. A 2-bit asynchronous upcounter has 4 possible states: 0, 0, 0, 0, 1, 10, and 11. It typically consists of 2 flip-flops connected in a manner that allows the first flip-flop to toggle with every clock pulse. The second flip-flop toggles based on the output of the first flip-flop, creating the counting sequence. It typically consists of 2 flip-flops connecting in a manner that allows the first flip-flop to toggle with every clock pulse, like possible states like 0, 0, 0, 1, 10, and 11. Logic diagram of 2-bit counter. The logic diagram of a 2-bit counter upcounter includes 2 flip-flops arranged in a specified configuration. The first flip-flop's output is connected to the clock input of a second flip-flop. Additional gates may be used to control the toggling behavior of the flip-flops. The logic diagram 2-bit counter includes 2 flip-flops arranged in a specific configuration. This is also known as logic diagram of 2-bit counter. Truth table for 2-bit counter. The truth table outlines the states and transitions of the 2-bit asynchronous upcounter. Each row represents a current state and the next state after a clock pulse. The table shows how the counter increments from 00 to 11 and then wraps back to 00. Each row represents a current state and the next state after a clock pulse. The truth table outlines the states and transmission of the 2-bit asynchronous upcounter. 3-bit asynchronous upcounter design. A 3-bit asynchronous upcounter can represent 8 states: 0, 0, 0 to 1, 1, 1. It consists of 3 flip-flops, where each flip-flop's clock input is driven by the previous flip-flop output. This cascading effect allows the counter to increment correctly through each binary state. It consists of 3 flip-flops, where each flip-flop clock input is driven by the previous flip-flop output. A 3-bit asynchronous upcounter can represent 8 states: 000 to 111. The cascading allows the counter to increment currently through each binary state. Logic diagram of 3-bit counter. The logic diagram for a 3-bit counter extends the 2-bit design by adding an additional flip-flop. Each flip-flop is connected in series, where the output of one serves as the class input for the next. Logic gates may also be included to manage the reset and control signals of the counter. In the logic diagram 3-bit counter, it extends up to 2-bit design by adding an additional flip-flop. It can add additional flip-flop into 3-bit counter. The counter sequence programs for 000 to 11, demonstrating the binary counting principle. Truth table in 3-bit. Advantages of asynchronous counter. Asynchronous counters are simpler in terms of design and implementation compared to synchronous ones. They require fewer components, making them cost effective for basics counting application. However, they may have a slower response time due to ripple effect of single preparation. If they synchronous counters have very slow response due to ripple effect or signal propagation. Application of asynchronous cursor. Asynchronous up counters are used in digital clocks, frequency dividers, and event counters. Their straightforward design makes them suitable for applications needing basic counters functionality. Understanding their operation is crucial for designing more complex digital circuit systems. Feel free to modify any of content or formatting as needed. Thank you.